everybody. Thanks for coming. So recap. Over the last 3 weeks, we talked a lot about. Hello? Thank you. We're a small group, so I hear everybody. So thank you for attending. So we talked a lot about the multiple regression model and the least square estimator, and about its properties. And we saw that there was a lot of classic properties, right? We saw that under which assumptions the least square estimator was not only linear, very practical, it was also unbiased. We saw under which assumptions it was at least consistent. We were even able to calculate the variance, the covariance matrix of the least square estimator, at least under the so-called classical or standard assumption of the linear regression model. So heterogeneity of the regressors, and look here, that was here very important, obviously, that we assumed so far that the residuals were homoscedastic and not autocorrelated. So that the covariance matrix of the residuals were just a diagonal matrix with some sigma square. And sigma square was the variance of each individual residual, right? Okay, so far so good. Next question was, well, yeah, okay, the square estimator under these assumptions has nice properties, biasness, and so on, and we are able to calculate the variance, but could we do better? Or in which cases can we do better? And for that, it was obvious to me that if we have an unbiased estimator, then we're interested in small variances, right? Because unbiased means on average we are on the right track. There is no systematic under and overestimation of the true parameter by our estimator, and therefore we want to have that the fluctuations around these true parameters of our estimator are as small as possible, right? If the variance of the estimator would be 0 in the extreme case, then we would hit the true value with certainty. Okay? So the smaller the variance of an estimator, the better, if it is an unbiased estimator. Okay? And this brings us here we talked about some criteria, how to prove that it's a consistent estimator. Here, blah, 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 blah. The Gauss-Markov theorem. That's the next cornerstone. The Gauss-Markov theorem says that under heterogeneity here, and under the assumption of the so-called classical assumption of the linear regression model, you can't do better. If you're interested in a linear estimator, and we discussed that why it's so nice to have a linear estimator, and if you're interested in unbiased estimator, well, yeah, also a nice property, then you can't do better. In the sense that the variance of any other linear unbiased estimator is at least as large as the one we calculated for the least square estimator. Okay? This is what means that it's an efficient estimator. Yeah, this is why we call it efficient. Here a few notes about the interpretation of that. Well, first of all, it states this theorem, which finally justifies why we spend so much time on the least square estimator, because it's simply the best under some assumptions, right? That this is not only an asymptotic thing, right? But it's a finite thing. Well, we will see in the proof. Well, give me a number of observations, and for each number of observations, it holds. It doesn't hold only for n goes to infinity or something like that. Okay. We will also see in the proof that it does not require here. It only requires here the classical assumptions in the sense that it has to be homoscedastic and free of autocorrelation error, but it has not to be normal. In the next subchapter, when we talk about confidence bands and testing and so, we often make the assumption for simplicity and for other reasons that we have normal errors, but the proof works well without it. If U is normal, you can show, if you are more interested in mathematical statistics, there is something called the Kramer-Rao lower bound. So if you have if you don't look only at linear estimator, but in a more general context about estimating that parameter, one can prove that there is some lower bound for an unbiased estimator, and this is called the Graham-Rao lower bound. And in the very special case that it is normal, or you can even see that this is really the optimal estimator, right? So there is no non-linear estimator which is unbiased, which is even better, which has lower variance. All right, okay, so here's proof. And this, I guess we discussed already last week. So if you look at the proof, I think, up till here, the proof is very easy. Yeah, it looks maybe impressive for you. I don't know how familiar you are already with matrix multiplication, but actually it's not more than this, right? Let us check here. This is a linear regression model. Let's assume that we have an alternative estimator, right, which is linear, so we can, if it's linear, this means that we can write it like this. You see the least square estimator has also this structure. In that case, A is just x, y, blah, 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 right? More complicated matrix. If it's unbiased, that means that its expectation is just beta. And we see that from linearity and unbiasedness, we already can say that, well, that this matrix A, which defines this alternative estimator, that it must be somehow orthogonal here to the matrix X. So AX is the identity matrix, right? And the rest is just, applying the rules for, matrix multiplication and for covariance matrix. So this is just, for simplicity, for convenience of the proof, we now define the difference between these alternative matrix and the least square estimator. This is the A in case of the least square estimator, right? And if you just multiply with x, you see that dx is 0. Okay? So, and now we calculate the covariance matrix of beta tilde. Right? And when we do this, right, we just plug in what b tilde is, that's a y. So if you now plug in the model, yeah, well, this is not random, beta is not random, the only randomness here is u, so it's just AU. In each step, you have the opportunity to raise your hand and ask. Right? Okay. So here we apply the very general rule. What is the covariance matrix of a matrix time a covariance matrix, right? So this is always A variances. You see that this rule here for matrices, we already applied that, I guess, is somehow a generalization of this very simple statistic 101 rule that if you have a random variable x, and you want to calculate the variance of it, then the variance of 5 times x is 5 squared times the variance of x. Right? And here you see the square, A transpose. Okay, so now you see that how important it is to have this classical assumption here in the proof. Well, if you remember the proof for example, unbiasedness or so, right? We checked the proof and we saw, well, actually we don't need that the residuals are homoscedastic, for example, right? The proof doesn't need that. So obviously, the least square estimator with exogenous compressor is also unbiased in case of heteroscedastic cases. Here, this proves really you make use of the assumption that the covariance matrix of the U is a diagonal matrix. This is why this is just sigma squared A times A. Alright? So Gauss-Markov really needs this assumption. If you don't have this assumption, it is wrong. Right? And in fact, later in the course, we will remember you, we will call you to do how the properties of the least square estimators are if some of the classical assumptions like heteroscedasticity and population and all things do not apply. Well, then we talk about the generalized least square estimator, and because of the least square estimator, the ordinary least square estimator we deal with so far is not optimal anymore. Okay, but here, classical assumption, sigma square identity matrix, and now look, we just apply what, well, we saw that A here, if D is like this, then A is D plus this. Okay? We just make use of this definition. So D plus this, and then we multiply it out. Now it's really just matrix multiplication here. Now you see how everything cancels out here. Well, dx is 0, right? That goes away, that goes away. The only thing that remains is this here. And now we see that the covariance matrix of the alternative estimator is the covariance matrix of the least square estimator plus something. And if you're naive, you might say, plus something, so obviously, therefore, this proves somehow that this is somehow larger than that one, right? Because we add something. But it's not as simple as that, right? Because these are matrices, so I don't know, is this negative, for example? So I have no, it's not clear, right? So what we have to talk about a little bit in order to make this last step here, to understand this final step, is how to compare the size of covariance matrices. How to compare, well, if you have two numbers, it's obvious why one number, this number is larger than the other one. If you have two matrices, right, it's not so obvious. It's not obvious at all. Right? When you can say this matrix, this covariance matrix, for example, is larger than the other one. Right? So, as you see, this here, in order to understand this here, the last final step here, we have to remember, or I have to know, what positive definiteness means of matrices. So we have to make sure that we understand how to compare matrices, right? And in order to say a few more things about that, I included here additional slides on Blackboard about, say, recalling what does it mean that matrices are positive definite. Okay, I often say recall because I teach that in the first semester in math at Gefei-FIONA, but of course only 20% or so of you have done the bachelor at Gefei-FIONA, so let's complete it. Or is that already known to everyone? Okay, let's see. It takes only 7 or 6 slides, so it's relatively easy, I would say. Okay, so the first thing, the first definition, well, that sounds now very abstract and technical somehow, but it's not a big thing. Let's consider a symmetric square matrix. That's fine because we are interested in comparing covariance matrices, and we know covariance matrices of a vector, the covariance matrix of eta hat, right, is of course a quadratic matrix, and it's symmetric, right? Each covariance matrix is symmetric because covariance of x and y is the same as between y and x. Okay? So this is exactly the situation we're in. We want to talk about quadratic symmetric matrices. Yeah? Other matrices are not interesting for us. Now. Okay. So you see that if you have such a matrix, you can define something which is called the quadratic form. And now you see why it's quadratic, because you have 2 times x. So if you just take one vector here from the R, from the n-dimensional plane, some vector x size n, like our data, right? So then you can define x prime ax, and if you look at the dimensions of these vector times matrix times vector, you see that the result is a number, right? Because you have a vector x, but you transpose it, so you have this one, then you have a square matrix, and then you have the vector here, like this. And this gives you more or less a scalar product, like this, which results in a number. Okay? If you feel uncertain about that, just make the numbers here. This is n times 1, this is n times n, this is 1 times n because it's transposed, And if you multiply this out, you see, it's a number. It's a 1 times 1 matrix with columns. Okay? Therefore, it makes a lot of sense to say here this is larger or smaller than 1. Right? If you have a matrix, it's not so clear what you mean with this. The matrix is larger than 0. What do you mean? Right? Number, no problem. Okay, so we look at matrix multiplications like products like this one. And you see that, well, in a sense, we already work with this kind of quadratic forms without calling them quadratic forms. So here, 2 special cases. Assume that A is just the identity matrix, right? A is quadratic, A is I is then symmetric, quadratic, so all right, okay? Somehow a trivial thing. So what is the quadratic form that belongs to the identity matrix? You see that then we have x prime identity times x, so we have this. And what is that? This is just the square of the length of the vector. The inner product of the vector with itself. Okay? And another interesting special case for us, for every matrix, suppose you have an arbitrary matrix. So m, n. Maybe it's even a vector, right? Then it's 1 times n. If you multiply it with its transposed, remember x prime x and all these things, right? Then it results in a symmetric n times n matrix. Okay? Okay, symmetric n times n, so you can apply this thing here. You have the quadratic form that is associated with that. And it looks like this. Alright? So the definition of a quadratic form for symmetric quadratic matrices is not so special as it looks like, right? Because if you have any matrix A, you can define a quadratic form like this here. Okay? So now, here we are already at the definiteness. Because originally, the mathematicians talk about the definiteness of quadratic forms. So this is a very general concept. But we apply it, not only we, but in most cases, this is the most important application, we apply definiteness here to the corresponding matrix. So look here. We have a symmetric matrix, and we call this matrix, right, positive definite if, look here, this number which comes out when we multiply, when we apply this quadratic form to x, so if we calculate x prime ax, when this number is larger than 0, all non-zero vectors. So whatever because you have to say this, because if x is 0, if x is just a vector of zeros, then of course this is 0, right? 0 times something is 0. Okay, so that's a trivial case you have to put aside. If you do that, if you say, okay, I only look at non-zero vectors now, because this is a trivial case I'm not interested in, then this looks, well, whatever vector you take, right? X can be full of negative numbers, right? But if you look at the quadratic form, then everything is larger than 0. For sake of completeness, I also put here what negative definite is, you see, or well, what indefinite is. Well, it's indefinite and it's neither positive nor negative definite, right? And there are matrices out there which are neither one nor the other thing. Well, sometimes, especially if you look at microeconometric theory books, they talk about semi-definite matrices, and this is just if you allow here for equal sign. Okay? In our applications, positive definiteness is a concept you may be interested in. But all the math I show you on the next 2-3 slides, you just have to, it obviously also applies, or it naturally applies to negative definite matrices. Alright, so where the application of this positive definiteness thing, where might you have heard this already, or maybe you will heard it already, or in the next months? So there is, the first time I came over it was in Micro 2. So in advanced micro, right? You heard that in advanced micro? Right, you know, if you have a multivariate function, so demand depends on several prices or whatever, right? If you want to maximize or minimize this multivariate function, then there are the first order conditions, right? The partial derivatives have all to be zero, stationary points, and all things. But then you want to know, is it really a minimum or a maximum, or maybe a center point? And then you have to look at the matrix of the second order derivatives, right? It's called the Hessian matrix. Hesse was German, I guess. Right? So, and if you remember, if the function you're interested in is continuously differentiable, so in most cases when we apply it, right, here in economics, then the Hessian matrix is quadratic by construction and symmetric, right? So it makes sense to talk about the definiteness of the Hessian matrix. And in fact, the sufficient condition for extrema, minimum or maximum, is that Hessian matrix at that point, if you evaluate it at that point, positive definite or negative definite or what? Okay? So this is one application in way needed in micro and macro. We apply it here because covariance matrices are, as we will see, always positive definite. So covariance matrix, what we already know is covariance matrices are quadratic, covariance matrices are symmetric, so yeah, it's well defined. We can check, it makes sense to check the definiteness of a covariance matrix, right? But what we will see in a minute with all covariance matrices are positive. Alright, so look here for example. Yeah, why is that so? Here's already the proof, we would say, right? Why covariance matrices are always positive. Consider a vector of n random levels, like our n errors, u1, u2, u3, un, our vector of u, right? Of errors. And for simplicity, assume that the errors have expected value 0. Okay? So then, what is the covariance matrix of that vector of a random variable? You only get used to that. This is the expected value of the outer product of u's. This is a matrix, right? If there was u prime u, it would be the inner product, which is just, it would just be a number. If you put it like this, you have the outer product, the matrix. In fact, this is the covariance matrix. And now look what happens if you multiply and this matrix here, if you just check for definiteness of that. So what you have to do is, well, let's check. We have some x non-zero, and you multiply from the left, and you multiply from the right. Let's see what comes out. Right? If it's always negative, then it's negative definite, always positive, positive. If we can't say anything, it might be this or that, then it's indefinite. Here's a trick. Look. The only thing here you apply is in German it's the Assoziativgesetz. I don't know the English word for it because I learned my math in German. So every now and then I miss the English vocabulary for math. Is this the association? Law of association? So here, look, you could switch the parentheses, right? So A times B times C. Well, it doesn't matter whether you first multiply AB and then C, or if you first multiply BC and then A. Right? Okay? So this is what we do here. We just put the parentheses differently, and then you see here that this here, x prime u is nothing but u prime x transposed. Yeah? Remember this rule that AB transpose is B transpose times A transpose. Right? We already applied that. So this is just the rules for transposing matrices. And now you see, you have here the same vector. You have the inner product of the same vector. This is just the length of that vector. And the vector, which is non-zero, is always larger than 0. Okay? So, covariance matrices are always numerical optimization out there is the resulting covariance matrix is not positive definite, or not negative definite, or something like that, right? These are the numerical properties, because they have to be positive definite if it's really a covariance matrix. All right. So we have, so every covariance matrix is positive definite. What does that mean? How can we characterize positive definite matrices? And here's a nice trick. So here you see a necessary condition for definiteness of matrices. So now think about, I just give you a matrix here, and I ask you, is it positive definite or not? Could that be a covariance matrix of a random error or not? Right? Here's a necessary condition. Immediate implication of the definition of positive definiteness. Positive definiteness means whatever x you take, non-zero, this is positive. This is the definition of positive definiteness. Okay, for every x, okay, let's take a specific one. Let's take this vector ei, I guess we had that already, here. The vector is somehow the unit vector, which is 0, but always 0 with the exception of the i's component here. Okay? Einheitsvektor in German. 0, but only 1. And now apply this here, this very general condition, because we assume that A is positive definite. We apply this for this very special vector. Okay, if it holds for everyone, then of course it also holds for the special one, right? So, but what happens if we apply this very general thing here to the very special vector? If you do this, what comes out here is just the i's diagonal element of that matrix. Okay? Here. This is AII, so A11 is in the upper part, and A12, A13, and so on, right? And you have A22, A33, these are the diagonal elements. Okay? Try it out. If you don't believe it, try it out. Make a simple example and try it out, and you see what comes out. It is very important. Therefore, right, we have already a necessary condition to see whether a matrix is positive definite or not, whether it can be a covariance matrix or not. So if A is positive definite, then all the elements of A are positive. If I gave you a matrix and one of the diagonal elements is not positive, then it cannot be a covariance matrix. It cannot be positive definite. Right? That makes a lot of sense, right? Because the diagonal elements of the covariance matrix are the variances. And variances should be positive, right? So, all right. Now we come to the question, which started our interest in positive definiteness, so to say. How to compare covariance matrices. Remember, in the Gauss-Markov proofs, we said, this one is larger than the other because something is positive definite also, right? So obviously, this gives us a criteria to compare covariance matrices. Look here, and this is it. So, suppose now we have two alternative unbiased estimators. Exactly the situation of the Gauss-Markov. We want to compare the covariance matrices of two unbiased estimators. So, and suppose these matrices are like this, right? And we call the covariance matrix A and B. So, what does it mean? Consider now the difference between these two covariance matrices. This is exactly what we do in the proof of the Gauss-Markov. We consider the difference between the alternative estimator and the least square estimator. Suppose this difference is positive definite. What does it imply? Well, we just saw this implies that all the diagonal elements of A minus B are positive. But what is the diagonal element of A minus B? It is the diagonal element of A minus the diagonal element of B. Right? Adding up matrices is easy. Right? if we can show that A minus B is positive definite, that implies that all variances of A are larger than those of B. Because under diagonal are the difference of the two variances. And if this difference is positive, then obviously the one is larger than the other. Right? For all the E's. And in this case, we call A is less efficient than B. Because both are unbiased, as we assume it, right? And all the variances of A are at least as large or even larger, if it's really positive definite, it's basically larger than those of B. Okay? So this is the criterion that gives us a sufficient condition for this estimator is more efficient than the other. Because all the diagonal elements of the difference of the covariance rate are positive, meaning that all variances are larger than the variance, or smaller, larger than the others. So here in the Gauss-Markov theory, we had the covariance matrix of the alternative estimator, some k times k matrix, minus the covariance matrix of the least square estimator, sigma square times x prime x inverse. We showed that this is this matrix here. And now you see, it doesn't matter what D is. It's always D prime D is always positive definite. Right? Look here. X prime this, prime that. Did I make a mistake here with a prime? Probably. Let us check in the proof. Maybe this is a typo here. So this is x prime d, and the same argument applies as we did before. Here, this here is just the inner product of two non-zero vectors, which is always positive. Okay. So that's it. So let's check. Let's go back for a second to that proof here. See, same typo. Obviously, I copied. So this is yeah. Look here. This is the D and not D prime D here. Yeah. So that's the typo. So this here is always larger than zero. And here I call it the vector v, the other side I call the vector x. I think you're flexing enough. Don't be confused. Okay, so this completes the proof. Alright? So this is why we say, it's positive definite. Check. Therefore, the variances here of these alternative estimators are all larger than those of the least square estimator. That's it. Okay? So, a final comment to these positive definite thing here. So, look here, a simple example. So, of two matrices, they are quadratic. They are, these star means that they're both the same number, so they are also symmetric. Okay? Quadratic, symmetric. So, question, what about the definiteness of these two matrices? What can you say about them? Right? If you look at A, you can immediately say, well, this matrix is nothing. This is neither positive nor negative definite. Because we showed that a necessary condition for positive definiteness is that all diagonals are positive. They're not. Right? So this matrix here, whatever you assume about the stars here, you can put any number in the stars, it will never be a covariance matrix. Right? Because it would imply a negative variance. Makes no sense. Okay? So, same, of course, it also cannot be negative definite, right? Because you have a positive number. So if you would be a microeconomic theorist, and this would be the Hessian matrix of your second order condition, then you would say, it's a saddle point. neither minimum nor maximum, it's a saddle point, because it's infinite. Okay, so what about here? This matrix is possibly, could be positive definite, because the necessary condition that the diagonal elements are both positive are fulfilled. Okay, that could be. Right? However, and this will be discussed by Leah in the tutorial, this is not a sufficient criterion. Okay, so whether this here is positive definite or not actually depends on the eigenvalues of the matrix. Did you recap eigenvalues in the quantitative how is it called now? Quantitative pre-course? Probably, probably not. Okay, so Leah will just give you a recap, 10 pages or so, about eigenvalues matrices. And this is, this looks very, this is, deep, right? But the beauty of these things here is that you get, you have a little mass and you have a lot of results, right? Like here with this, we had one definition, what is positive definiteness, and then we just look at whether something is positive or not, and we know it's minimum or maximum or covariance or not, we have a lot of results, right? It's not like in calculus, where you have nitty-gritty details, complicated proof, blah, 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 and then, pages from calculations, Okay, it's really nice. All right, now look here. This here is a matrix that should motivate you, well, to learn what eigenvalues are for the matrix. So here we have this matrix, that's the condition fulfilled, and here you have two examples. Now we plug in here two examples here for the stars. Look here, this is here, symmetric, quadratic, positive, diagonal, same here. This matrix is positive definite because the eigenvalues are positive. May I tell you? This here is indefinite because there is a positive and a negative eigenvalue. Don't believe it? Check out. If you have a non-zero vector like that one, you do the test, x prime v times x, the result is minus 2. Right? So it is not positive definite. Can it be negative definite? No, why not?
Positive numbers on the diagonal?
Yeah, thank you. Thank you for being awake. Good. Great. Okay. So that's the the very basic eigenvalues and eigenvectors, form the very basis of linear algebra. So a lot of results in econometrics and also in dynamic macro. In the end, you linearize your models, meaning you talk about matrices, meaning you talk about stuff like that. Okay. All right. Now we understood why and under which assumption, in particular, the least square estimator is efficient. So, in the class of unbiased linear estimators, so it makes sense to talk about it. All right, go ahead. So, now, next step is we want, these are theoretical results. Why do I emphasize this? Because, sigma square, and here and when we derive the variance covariance matrix here, where is it? Okay, right? We want to talk about the precision of our estimation. We want to quantify our estimation of certainty. The answer is, the theoretical answer is, look at the covariance matrix of your estimator, right? On the diagonal, there are variances. That will give you, in the end, confidence bands and tests and all these things. Thank you very much. Here is the matrix. I don't know what sigma square is. Well, thanks for nothing, right? I can observe the x prime x, blah, 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 blah. But what about sigma square? I don't know. Okay, I have to estimate it. Okay, there seems, you know, sigma square is a variance of the errors. So we already have some idea how to estimate it, right? If the estimator beta is nice, so it's unbiased, the u-hats we calculate from our least-square estimations, and the unobservable u's, and we are talking about the unobservable u's here, they are somehow related, right? They should be close. So the question is, how are they related? We want to know what is the variance of the u's, because then we are really able to plug down numbers for the variance of our estimations, right? In order to be able to do that, we have to have an estimate for sigma square. Otherwise, it's not possible. Okay? We know sigma square is the variance of the u's. The u's we can estimate consistently, unbiased, with our least square estimations, which gives us the u-hats. So let's somehow take the u-hats and look how the covariance matrix of the u-hats, this is one we can see from the data, right? How is this matrix related to the unobservable covariance matrix of the u's? This is the trick, how to estimate sigma square, how to get an estimate of sigma square. So, here we are. So, look, we want to talk about u, okay, but the only thing we can observe is u hat, the estimated residual. Well, so we know u hat is y minus x b hat, beta hat, and now, well, now comes this projection thing again, right? So you remember from section 2, 3, whatever, you know, this is the matrix M. This was this allyl matrix, right? So I minus P, projection matrix, times Y. So we call this just M. This here, the matrix M, and you get an X, you know, in order to make clear that the root everything are the regress with X. This is a matrix that relates the unobservable u's we can't observe to the observed u hats. Right? So, what does it mean now? Now we have a relation between u hat and u, nice. But we don't want to talk about the u hats. We want to talk about the covariance matrix of the u hats. So how is the covariance matrix of the u hat related to the covariance matrix of the u's, which we're actually interested in? So, look here. If u hat is mu, then the covariance matrix of the u hat, something we can estimate from the data, is m times, oops, no, is left. Then the covariance matrix u is just, look at again this rule, right? M times the variance squared of u times m transpose. A question.
Why is mxy the same as mxu?
Here, yeah, if you just look, if you have, what we did is, if you multiply this out, you have y, right, here. U hat is y minus, this is the definition of u hat. If you multiply that out, you see this is y minus, and now you, because you know that it's, you plug in y is x beta hat plus u. Yeah? If you plug in what you know about y is x over, and then you multiply out, and then you see that it's just canceling out. Right? So it is x beta plus u. So here comes the true model inside, right? And then you see that this just cancels out by multiplying. Too quick? Okay, it's really just plugging in x beta plus u and then multiplying out. The only thing that's left is m. Yeah? So, now this is again this rule we just applied also for the covariance matrix thing in the determinateness, right? So if you have a random vector, if you multiply that vector with some matrix, the resulting covariance matrix of that new vector is just this. So, the covariance matrix, so this could be a large V, sorry for all these typos. Large, so this is the covariance matrix of the U's. This is just sigma square I, right? So this is sigma square identity. So it's just sigma square times m prime. And now if you remember when we discussed the geometric interpretation of the least square estimator, right? We call that this matrix M here, which you can easily prove here when you look at that. This matrix M is symmetric. So M transpose is the same as M. And it's also idempotent. So it's a projection matrix. M squared is M. Okay? This is why this second M here somehow mystically vanishes. Right? Because of the M square M thing. Alright. Great. Now we have a relation of the estimatable covariance matrix of our residuals, right? We plug in the data, we solve the square estimator, then bam, here's the estimated covariance matrix of use, no problem. And the matrix M is also observable because it's just, this is a matrix, we just need to know our data, that's it, right? The only thing which is problematic that this is a parameter we after, right? So now, how can we use this identity here, this relation between U hat and U,